Hi folks, it's Mr. M here with another video. This time we're talking about function transformation, so continuation from the previous video looking at function transformations and reflections based on from the parent function. So we looked at the mapping rule last video, and in this lesson we are going to continue on with that mapping rule and looking at what are the transformations applied to my function, and then how I can transform that parent function to sketch the graph of my new transform function. So if we take a look at this function right here, the first thing we want to do is identify what the parent function is. So right now we could see there's an x squared, so the parent function is f of x is equal to x squared. And then we could start to look at the mapping rules. So if we start with x and y in the original y equals, or f of x is equal to x squared, we could see that here there are no transformations directly applying on the x, because meaning there is, like, if you think of f, well, here's like the analogy. If you think of f of x as being equal to x squared, well then really this part right here, like that x, that input is the thing being squared. So there's nothing inside that bracket, that imaginary bracket, that is like there's no 2 here, there's no +3 here. Like those things would affect me horizontally. Those things would affect my input. I don't have anything like that here. These numbers, the -2 and the 3, are outside that imaginary bracket around the x, around the input. So these things are what are affecting me vertically. Like this would be the a, and this would be like the value that's like the d value that's dictating my vertical translations. So I don't have anything in the x, no transformations in the x, so my x coordinate stays the same. However, in the y, this -2, so that negative number is is a reflection across the about the x-axis. So I'm gonna multiply the y by negative, and also it's a 2, so it's gonna stretch by a factor of 2. So it's gonna flip and it's gonna stretch by a factor of 2. So my y becomes -2y, and then I'm translating everything up 3, so I get +3. So that's my mapping rule. And now I can just apply some coordinates, like if I were to first sketch my parent function, on x squared, I have 0, 0, 1, 1, 2, 4, and the opposites. So I have -1, 1, -2, 4, and so on. If I take 0, 0, I'm gonna apply the mapping rule here. So 0 stays 0, and then the y, well, it's -2 times y, so -2 times 0 plus 3, which just reduces to 3. So my new vertex for this transform function becomes 0, 3, which is right here. Likewise, if I do 1, 1, well, my point's going to end up being 1 for the x, so right here on the x, so on this x coordinate, and the y coordinate is going to be -2 times 1 plus 3, which is just which is just 1, right? -2 times plus 3, which is just 1. So I get this point right here. Due to symmetry, I know that the axis of symmetry for any quadratic goes through the vertex. So if this point is right here, then by symmetry, the other point has to be equidistant from that axis. So right here, right? That's just the balance of this line, right? So if it's here, the other one has to be there. So I don't need to actually plug in -1. If I do, I would probably end up, I would have to end up with 1. Okay, so good. Moving on here, I could try 2, 4. So this point right here, see that where that translates to. I'm gonna apply for x, it's gonna be 2, and then y, it's gonna be -2 times 4, which is my y, right? 4 plus 3, which that would be -8 plus 3, so -5. So that point right there, and the other one would be here. And now I could connect them. Okay, so this right here is my transform function. This is the parent function. Now, there is an easier way to go about this. It's a little bit intuitive, but the alternative way to doing this is to pick any point, let's say the origin, and then going about the transformations in a logical sequence. So right here, first I'm going to flip, so reflect about the x-axis. So if it's 0, reflection just stays the same. Now I'm going to stretch it by 2. So if it's 0, it's on the x-axis itself, and there's no stretching, so it's just 0. And then I'm just going to shift it up 3. 1, 2, 3. So I end up here. Right? So that's how you can do it piece by piece. So let's take this random point right here. So on the parent function, 2, 4, right? I'm going to first reflect it, right? It's a vertical reflection, meaning it's reflected about the x-axis. So 2, 4 becomes 2, -4, right? The y-coordinate flips, but the x stays the same. And now it's stretched. So it's stretched by a factor of 2. So it's going to go to 8 over here. So it's going to go to 8, right? Because it was -4. It doubled to get to -8. And then it's going to shift up 3. So 1, 2, 3. And I get to my point right here, 2, -5. Okay, so that's how I could do that very nicely. And when you get good at that, you can apply the mapping rules just on the fly like that. So that's good. All right, let's take a look at this. This is the absolute value function. This is like the V shape right here, the characteristic V shape. So it's just 0, 0, 1, 1, 2, 2, and then the opposite's -1, 1, -2, 2, and it looks like that with that arrowhead. So now I'm going to look at this transformation right here. So on the parent function f of x, which is the absolute value function, I'm applying triple. So I'm like the y value, each y value is getting tripled, as we can see here, and they are decreasing by 5, like that. And in the x, the only thing is happening is that it's a rightwards shift of 4, right? With the x, it's the opposite that it looks. So if it's x -4, it's actually a shift to the right of 4 units. So that's the only thing. And notice here, this is inside the brackets of the input. Hence, that's why that -4 is affecting me horizontally, whereas this -5, it's outside all that internal action. So it's affecting me vertically, my output. Okay. So I can go ahead here with that 0, 0. Let's try the, like you could see the formula here for the mapping rule. Just plugging in 0 here and simplifying, I get 4. I'm plugging in 0 into y here and I get -5. So 4 and -5. Let's prove that using like the intuitive way we learned. So I'm just going through these transformations here. So with the 3 first, I stretch, but it's at 0, so it stays the same. I'm shifting 4 to the right, so 1, 2, 3, 4. And I'm shifting 5 down. 1, 2, 3, 4, 5. All right, well, I get where I am. So that just takes a matter of seconds when you get practice with that, right? Let me pick another point. Let's say 2, 2, right? I haven't even done this one yet here, but let's just verify that it's actually on this line here. So 2, 2, all right, so I'm gonna first stretch that by 3, so it's gonna triple, so it's gonna get 2, 6 right here. And then I am going to, so after I've tripled it, I'm going to shift it 4 to the right. So 1, 2, 3, 4. And then I'm going to shift it 5 down. 1, 2, 3, 4, 5 right there. And look at that, lo and behold, I get a point on my absolute value function, the transformed one. So very good. So I can verify all of my points that way. Okay. And again, the symmetry, like the pattern applies here. If I draw like a line of like right down the middle, that's the axis of symmetry. So any point, if you find the right side, you could just get the left side by finding equidistant from there. So here, notice I found this point right here, down the middle, 2 units this way, hence 2 units that way. So that would also be a point on the absolute value function due to symmetry. Okay, all right, moving on. Here I have the here I have the square root function. That's the parent function. So f of x is equal to root x. Now, you got to be very careful with the insides of things, not because this is a square root, but in general, when we're dealing with x, we just have to be very cautious because not only does x's behave differently, like with the opposite signs here, these coefficients can also be counterintuitive. So we're going to learn all about that in a future video, in a future lesson. But for now, we're just dealing with reflections. What you have to know, regardless, is if there is a coefficient or a sign on the x inside the square root or inside the input of the function here, I have to factor that whole thing out. So here I'm factoring out a negative, and in the bracket I get x -5. Now this corresponds to the correct translation horizontally, okay? So that's why I have to factor out that negative there from both terms, okay? So that's what that says right here. And now I can apply the mapping rules, right? This is a stretch of 2 vertically, hence it's affecting the y. And then these are horizontal, so I'm going to stick with vertical. There's a shift down 3. So right here, that's the vertical transformation. Horizontally, well, my x gets multiplied by just negative 1, because a horizontal reflection is like left to right. So it's across or about the y-axis, and then it's shifting 5 left, 5 to the right rather. So then I get negative x plus 5. Okay, so let's plug in a point here. We could see here when x is 0, we get positive 5. When y is 0, we get negative 3. So my point is 5, negative 3. Right here, 5, negative 3. I could put a point right there. And keep in mind, the square root function, parent function looks like this. 0, 0, 1, square root of 1 is 1, square root of 4 is 2, and it just looks like that. Now, if I were to transform this here, well, that first point is there, and then maybe let's take this point right here on the parent function, 1, 1. Let's transform that using our intuitive model now. So it's going to shift, vertically. There's going to be a vertical shift by a factor of 2, so it's going to double. And then there's going to be a horizontal reflection, so about the y-axis. So to get to right here, and then there's going to be a shift 5 units to the right. 1, 2, 3, 4, 5, and then 3 units down. 1, 2, 3, and voila, we get to that point. Likewise, we could do this again right here, double it, so I get to 4, and then reflect it along the y-axis, so I get to, so this is 4, 4, so I get to negative 4, 4, and then I could shift it 5 to the right, 1, 2, 3, 4, 5, and 3 down, 1, 2, 3. Nice, so I do get that. This looks correct. Okay, that's it. And if I did the math, I would end up with these points as well. There's one right here, which is the reciprocal function. The parent function looks like this. F of x is equal to 1 over x. Here, we don't have any stretching or compressing. We just have horizontal and vertical translations. So horizontally, this is an x plus 3. It becomes an x plus 3. And vertically, this becomes a y plus 5. So if I were to put this into words, what this means is that every x value on this parent function gets moved by 3 to the right and 5 up according to this transformation, which means even the asymptotes, because reciprocal functions have asymptotes, right? Let's say like the line y equals 0. So now my y is going to be plus 5, so it's going to be y equals 5. And likewise for the x, it was x equals 0 right here. So it's going to be now x is equal to positive 3, just like there. So those are my asymptotes. But again, my goal is not just to draw the asymptotes, it's actually just to draw the actual curve with the transformation. So I'll use some key, benchmark points on the parent function. So 1, 1 is a good one. And then I got 2 and a half, 2 and half, and then I got half and 2. And so I could use these points to get, so let's say I start here, I'm going to move 3 to the right, 1, 2, 3, and then 5 up, 1, 2, 3, 4, 5, right there. Likewise, 3 to the right, 1, 2, 3, and then 5, oh, am I doing this right? Yeah, 3 to the right, so 1, 2, 3, and then 5 up. So 1, 2. Oh, sorry, what am I doing here? I made a mistake. I'm looking at the transform function. Sorry, I'm supposed to look at the parent function. Oops, my bad. So I'm gonna shift this 3 to the right. 1, 2, 3, and then 5 up. 1, 2, 3, 4, 5. So right there, so on and so forth, and you're gonna get this side. And if you do this side right here of the parent function, you're gonna get the pink, the magenta down curve right there. Okay, so very nice. We have one more question right here, which is looking at, well, you have this type of function right here, which is a series, it's segments, it's pieces. Later on, we'll get to call this type of function a piecewise function, and we could do lots of cool stuff with this. But let's say we don't have a singular equation to describe it. We have it in pieces. So that piece from, that in that domain right there. And we got another piece in that domain from that looks like this, another line. And then from here, from x here to here, we got this. And from here to here, we got this flat line, right? That's how we define it. And we'll see more with piecewise functions in the future. But let's just start with a point right here, right? Let's say 7, -2. So that has the coordinates 7, -2. And I'm going to apply this transformation set to this entire function, right? Starting with the endpoints. So it looks like I have a reflection vertically, so about the x-axis. Then I have a vertical compression by a factor of a half. Remember the rule with the -x. I have to factor that out. So then it factors out from everything inside. And at the end, I have the -6, which is, well, here it's, here, that's a reflection vertically. So about the x-axis, this is a translation 1 unit right and translation 6 units down. So now if I apply the mapping rule, well, I get -x plus 1, and then I get -half, 1/2 y, which is, according to this, -6, which is what happened to the y, the new y. Now, if I plug these in, / if I do this with single points, I will get these new coordinates right here, right? Let's just pick a point here, 7, -2. I'm going to, for the x, I'm going to reflect it like horizontally, so meaning it's going to be across about the y-axis. So if it's 7, -2, it's now going to be -7, -2 right here. And now I'm going to move it 1 unit right. So right here, I'm done with my x transformations. Now I can look at my y transformation. So in the y direction, I'm going to compress it by a factor of -half. So first of all, a negative means this 6, -2 is going to become 6, +2. And then it's going to shift 6 down. So 1, 2, 3, 4, 5. Did I count that right? Sorry. 1, 2, 3, 4, 5, 6. It looks like I've made a mistake. Okay, so let's double check this. The point that we're under investigating is 7, -2. I'd love to just put it right here to make sure that it's correct. So -x plus 1, that's going to be -7 plus 1, which is -6. And then in the y, it's going to be -half to -half, and my point is -2. So that's going to be, yes, -6. That is going to be +1 - 6. So -5 is correct. Let's see. Let's just see. Made a mistake right there. So, so I'm going to take this point right here. I'm going to work with it horizontally first. So, sorry. I'm going to shift it. So reflect it on horizontally. So 7, -2 is going to become -7, -2. So right there. And then I'm going to shift it 1 unit to the right. So right here. Very good. -6, -2. And now I'm going to compress this horizontally by a factor of a half. So it's going to go right here, and then it's going to opposite sign. So it's going to go right here where the 1 is. It's going to reflect, right? Vertical reflection because of the negative. And then now it's going to, from here, it's going to go down 6. So 1, 2, 3, 4, 5, 6. Okay, so it is correct. It just looked a little bit weird on the graph, but you just got to be a little bit meticulous here. Okay, so we got that. And then if we apply this point right here, well, same idea, right? I'm going to flip it here. So it's going to be, what, 5? It's going to be -5 in the same height right here. And then +1 means I go this way. And then now I reflect it on, so if that's -2, that's going to be +2. I take half of that, so right here, and then I go down 6. So 1, 2, 3, 4, 5, 6. Again, there you go. I could connect these 2 points like this. And then I keep on going with these endpoints here to get to that one, this one to get to that one, I believe, and then this one to get to that one. Yes, it would have to be like that because these two connect here, and then here would be here, and then here would be here, and then here would be here. So that's kind of how that works. You could try it out with the mapping rules here that you see and make sure for yourself, or you could like do it the intuitive way. All right, that's all I wanted to say for this video. Here is the homework from the Nelson Functions 11 textbook for this lesson. Go give it a go, like give it a try, and good luck. Thanks and have a good one.